Okay, I think we'll get started. So this is the lab number 3 for Machine Learning for General Chemistry 2. And today we're going to be talking about unsupervised machine learning. And we're going to do so where we try to have the computer discover hydrogen bonding in a fake data set. So we're going to make this big database of these different molecules, and just by looking at the nature of some of the properties of the interactions of those molecules, the machine should be able to pick out, identify this special interaction, which we would then call hydrogen bonding. The key concepts here: unsupervised learning. So we're not going to tell the computer whether it's right or wrong. It's just going to use what's called a cluster algorithm to organize a data set and find out interactions that are similar to one another versus ones that are less similar. And when you inspect those different clusters, then you'll be able to see some kind of patterns emerging. And the ones we'll see here in particular are what we know in chemistry as hydrogen bonding. So whenever we have say an oxygen, something like a ROH, say N, something like that, R, then we would have a hydrogen bonding here. It's going to discover those patterns in this clustering. So this is a typical type of machine learning that's used for looking through large data sets and trying to find patterns. So the fake data set that we're using today, I just made up 6 different molecules, RO, RN, RC, or 6 different types of molecules, RC, ROH, RNH, and RCH, and they will have the normal rules of hydrogen bonding, but the computer won't know that. So I took 4,000 of each of these, and then with all possible pairings, made sort of random distances between the molecules and angles and energies suitable for when we have a hydrogen bond interaction versus when we don't have a hydrogen bond interaction. And so what we'll see then is, yes, this is artificial, but this is how the large chemical databases are searched sometimes when we use machine learning on those to find different patterns within those real molecular data sets. So this will serve as a sort of slimmed down artificial data set for us to learn those principles. All right, let's go to the lab, or to the computer. All right, so I kind of said much of this, but we'll see that there are some special interactions that arise, and we'll come to call those hydrogen bonding. This is, again, unsupervised learning, and we'll be using cluster algorithms. We'll be using both k-means clustering and hierarchical clustering, so 2 different models. So k-means and hierarchical clustering. This is by the way, this is the lab manual for this particular lab. Okay, here are our set of molecules, and we'll be looking then at molecule 1 plus molecule 2, and then getting a physical distance, angle, and energy, and this is all stored in a very large, just CSV file. Okay, so let's jump right to it. So let's go over to our Chem AI Street Part 2 launcher, and if you're just coming to this from this video, if you go to the very first video in this playlist, you'll see how to get this installed on your machine. We will then click hydrogen bonding. This one takes a while to load, so we just have to practice our patience here, and then it comes up. Okay, so we will load a data set. So we will go to where we have those data from when we downloaded and installed the program. And we're going to click on Molecular Interactions Data Set. And this has the 4,000 with all possible pairwise interactions. So it's loaded here. And now we're going to just work through the manual here. So the first thing we'll do is we'll click the Explore Interaction button. And so what we're going to see here is it's just going to choose a pair at random and then give us some distances and angles. And as we explore through this pair, we won't see any particular pattern, because looking at any one individual is not going to be able to help us discern any kind of special interactions that might be present. We'll also get a feel for these data, and we'll see that these just visually it would be impossible also to pick out. So first thing we'll do is just plot some histograms here, and you know, we do see some distribution of angles, so there tends to be a little more straight on than angled across this data set. The distance tends to be not too close, not too far away, but somewhere in between. And then we have this distribution of energy. But from this, it's really hard to tell, again, what any individual would be doing. We can change this to a scatter plot, and we can plot, say, physical distance on the x-axis and energy on the y-axis. And we'll, yes, normalize these features. And we see just basically a uniform distribution, right? So again, nothing that we can really pull out as something that we can say anything meaningful about, at least visually by eye. And so we'll use now the power of these clustering models to look at this. We'll do one more plot here. We'll just do a 3D plot of all three parameters. And again, very uniform, just no way to tell here. So these are just all these different points of pairwise interactions in this three-dimensional space of angle, energy, and distance. Well, let's go to the model, and we'll select k-means model here, and we're going to actually run this at 10 clusters, and you can explore the clustering. This is how many clusters it's going to break all those pairwise interactions down into. So we'll go ahead and run this, and it's scanning through the data set and then clustering these according to like values. Now it doesn't know anything about chemistry, it doesn't know anything about hydrogen bonding. It's just looking for things that are similar. And so we'll click OK. Part of the art of it is figuring out just how many clusters you need. So I think we'll see that 9 or 8 works pretty well, 10 works okay, and then we get less than that, then we start to not have as good results. Now, we're going to now move to results, and first thing we're going to do here is let's make sure our color by cluster, and then plot clusters. So we'll plot the clusters, and now we can see these are broken into 10. And we'll notice, you know, kind of a special one here. So this is how it decided to cluster these. And what we can then do is look at each of these clusters. So there's going to be 10 clusters, 0 through 9. And we will look at the distribution. And we see here nothing really special standing out. All the histogram is fairly close together, although we can notice these deficiencies here, and because we can anticipate, oh, this is hydrogen bonding, this might be a cluster that would not have hydrogen bonding. Now, we'll pretend we don't know that, and we'll say, well, there's not too much special about this cluster, other than we see some of these guys as perhaps being special because they're a little deficient there. And we'll look at cluster 1. Okay, now we're seeing those very same ones. Well, no, here's our CH and OH. Okay, so this is picking out not exactly a hydrogen bonding, but one with, well, at least from the Gen Chem perspective, one with a RCH. Hydrogen bonding is actually on a kind of a graduated scale, and typically in general chemistry, we say we need a nitrogen or an oxygen or fluorine there. Now here, this stands out pretty. There's a count of 2,000. It's all 4 of these molecules. So we know cluster 2 probably has this special, and these are standing out as special. Again, not too special, not too special, not too special, not too special, and 9. Again, maybe that that are sort of special. But this one, cluster 2, definitely special, really standing out above the rest. So let's show the cluster map. So it'll run through these, and as we see this definitely appears like right in that cone of hydrogen bonding. And look at this beautiful picture here. This is showing, this is the frequency of the position. Let me get this a little bit bigger here, if I can. The X and Y position here. So here is molecule 1, and then this is the closest atom in molecule 2. And we can see it's in this cone angle here and at about this distance, which says that, okay, there's a preponderance of these guys at this spot. And we see that, okay, that then must indicate some kind of special interaction amongst these molecules, which we call hydrogen bonding. Let's try one of these that was sort of okay. Like here's the OCH, so let's run a cluster map on that. Now, what will happen with the cluster sometimes, we got lucky sort of in this cluster. We'll find something like this. We'll find an adjacent cluster that completes this. And maybe we can find that, maybe cluster 3. Let's try cluster 3. Yeah, so perhaps cluster 3, maybe not exactly. Will be the sort of the symmetric image of that. Not quite. So that's kind of showing these molecules over here. And so that's the idea, is that you look for, in these clusters, you look for ones that really stand out like this as potentially special interactions. Let's go back. We need to go back to data. The hierarchical clustering takes a lot longer, and we're going to use a smaller data set for that. So we cut down on the number of molecules. And hopefully this will work and not crash the machine, but we'll choose hierarchical clustering, and we'll choose 10, and we'll run the clustering, and we'll see if it works here. Oh, shoot. Looks like it didn't. I am going to just, oh, okay, good. Yeah, sometimes it gets hung up. So let's see if we can just plot the clustering here. So that's a little bit different type clustering. Again, it was 10, I believe. So let's see if we see if this picks out a good one or not. So kind of, but nothing really standing out. Nothing really standing out. There, this one now starting to stand out, maybe not quite as pronounced, because on the k-means clustering, these were up around 2,000. Going there, we'll probably find a partner. Not really. Okay, so I think it was number 5. So we'll show the cluster map of number 5. This will be a bit more spread out probably than what we saw before. Yeah. So just a different way of doing the clustering. And this is an important area of machine learning and an important area in chemistry when we're looking at large databases. All right, so I think that's pretty much all I wanted to go through here. You can play around now by changing the number of clusters, getting a feel for what is too many, or what's a good number. Is there a number less than 10 but more than 1? Obviously, that would be a good number. And it does depend. Each time it clusters it slightly differently. The last time I ran it, I got my 2 hydrogen special interaction set kind of broken into 2 pieces, and you had to kind of look at them both together. But today we saw a really nice single cluster got all those, or got the majority of those interactions. All right, so that's it for this lab.